So today, like, we will learn about graphs. Okay, like, I don't want to be like, let's like, this class will be like little bit lighter side today. Okay, it's this is the first class, so I don't want to be like uh mm, information pack. So it's like a light. Okay, so I think the previous class we learned about the trees and like different type of trees, BFS and DFS, these kind of trees. So this is like extended version of trees, which is a graph. Okay, so basically we know tree. So tree looks something look like this. Okay, so tree have this structure which is like a root, we call it root, and they all are children, we call them children. Okay, they are childrens, and these are leaf nodes. These are leaf nodes. Okay, this is like a how tree look like. Okay, and how graph look like. So how graph look like? Graph don't have any root. Okay, and graph it looks something like this. Okay, this is how a graph looks. This is a graph. Okay, and it could be like this. This is a graph. So you can see they have a similar kind of structure, similar kind of uh like these. It's they like both have nodes, or we can say vertices. So these are nodes, vertices. Okay, and both have edges also. What are edges? Edges are basically these are the these are edges. These are edges. Okay, these are all edges. Okay, both have both the things, node and edges, but they look structure wise they both look different. Okay, and in trees we have a root, but in graph we don't have any root. So all you can select any of the node and you can start your counting, or you can start your traversal in any of the root, any of the node. Okay, so if you notice here, so there is like one famous line which is every tree is a graph, every tree is a graph, every tree is a graph, but not all graph, but not all graph is a tree. Okay, it could not be reverse, only one way. Tree could be graph, but graph could not be trees. And why it is it? Okay, and there's one more point which is like in graph we have a cycle. In graph we can have a cycle, but in tree we don't have any cycle. Okay, if you can find any structure look something like that and have a cycle, it's not a tree, it's a graph only. Okay, graph, a tree is allowed, tree, uh, any cycle is not allowed. This is the main difference. Okay, and here you will see every node have only two uh, childs or two nodes, but in graph we can see there is no particular order. Like it could be a, like could be a other n number of nodes attached to the single node. Okay, धीरे बोलेगा. Sorry. Okay, this is the main difference in graph and tree. Okay, let's go down, and we can say we have a adjacent node, and in tree, and in for traversal we have a same both same algorithm. For traversal we have a same algorithm which is BFS and BFS and DFS, which is breadth first search, breadth first search, and which is second is depth first search, first search. Okay, we can use both these algorithm on both of these for traversing, which is in tree or in graph we can use in both. Okay, and they work exactly same as in tree or as a graph, till they work exactly same, no difference. And in graphs we have a different types of graphs also. Okay, not a single type of, we have so many different types of graph, which is like, let's suppose we have a simply, this is one graph. You can draw a graph. Okay. Or you can say this is a graph. Okay, so this is a, we call it a cyclic graph. Why we call it cyclic graph? Because it's have a cycle inside. It's a cycle inside. So it's a cyclic graph. Okay, and we can say if no cycle is there, we can say acyclic graph. A cyclic graph. It don't have any cycle. So it will look like something like that. So it look like something like that. If it don't have any cycle, so it's look, so we will say it's a acyclic graph. Okay, so these are different types of graphs. Okay, and we have some few more graphs, which is like a weighted cycle, weighted graph. Weighted graph means we have some weight associated with every edge. Okay, so here let's suppose this is a graph. This is a graph, and then each edge have some weight. So let's suppose it's have a 2 weight, 3 weight, 4 weight. You can say this is a cost of going this node to this node is 4, going, and cost of going this node to this node is 2. This is a weighted graph. Okay, v1 and 2. And one more graph, which is a non-weighted graph. Non-weighted graph means it don't have any weight, so it could be like any graph which don't have any weight. So it's don't have weight, so it says, we can say non-weighted graph. Non-weighted graph. Okay, and then, so these are just different types of graphs, and we have few more graphs, which is like a directed graph. Directed graph means we have a direction. Direction means, let's suppose this is a graph. This is a graph. This is a graph. So it graph have a direction, which is look something like that. So look something like that. So we call it directed graph. Directed graph means we have a direction in it. So they have a direction in it. So it could be like this way also. So this is a directed graph. Okay. And same thing, which is a non-directed graph. Non-directed means we don't have any cycle. We don't have any cycle. So we will say non-directed graph. Look something like that. We don't have any uh, a direction, so we call it non-direction. And we can mix and match these things also, like these all types we can mix and match. Let's suppose we can create a cyclic directed graph. Cyclic directed graph. Okay, cyclic directed means it's have a cycle and it's have a direction also. So how it will look something like that. I'm just creating it now. Okay, it's looks, so it's have a cycle. So here it's have a cycle. Cycle is done. Then direction. We need to add direction also. So we can add direction here. So we can add direction. Okay. So it will look something like this. So this is a cyclic. We have a cycle inside. Then it's have a direction also, and then it's a graph. So it's a cyclic directed graph. Okay. And we have a one more very famous graph, which is we call it DAG, which is a directed acyclic graph. So we call it directed acyclic graph. Acyclic graph. Directed means it have a direction but don't have any graph, don't have any cycle, which is opposite to this one. So it's mean it's don't have any cycle, but it's have a direction. So we can create any graph. Okay, and we can add direction here. So it's mean it's have a direction but it don't have any cycle. So it's a directed acyclic graph. We call it DAG. It's a very famous kind of a graph type. We will use it in many algos. Okay, and then we have a one is disjointed graph, which is means we have a graph but which is not joined. So how it will look, it looks something like that. So suppose this is a graph. So we have a we have a this we have a two graphs. Okay, and we call it, this whole is a graph, but it is not joined. So we call it disjoint graph, because we have a full graph but is not joined together. These two are not joined together, so we call it a disjoint graph. Okay, means this is a one component, this is second component, it have a two components in it. We call it disjoint graph. And why we want to learn this thing? Because in future we have a algorithm which is called uh, disjoint union set. Disjoint union set, it's a very famous algorithm. We call it DSU. So disjoint union set, yeah, we call it this. This is very famous algorithm. We will use it in future. Why we use it, we will learn about later. Okay, so these are kind of a type of graphs we have in our system, we have in our data structures. And one second, yeah, we can have different types of graphs, which is like cyclic graph, acyclic graph, cyclic graph, then we have acyclic graph. These are just a theoretical part of this thing. Okay, because we need to know all type of graphs, otherwise like we not able to solve the questions. This is like a cyclic graph, a cyclic graph, a weighted graph. Weighted graph means we have some weight. This is a weight. Non-weight means we don't have any weight. And directed graph means we have some directions here, so you can see them some directions. These are directions. These are directions. And here we don't have any direction, so we call it non-directed graph. And then we have a cyclic graph, means we have a cycle in the graph, and which is a directed cyclic graph. So it's a directed which have cycle, so directed graph. Same with the opposite, which is like directed but acyclic, means we have directions but not a cycle, so it's a non-directed cycle. And then at the end we have this graph, this kind of graph, which is like a graph but it is not connected, so we call it disjoint graph. Okay, and then, so if you're wondering why where we use the graph, so like in Facebook we use graph. How we use graph in Facebook means, let's suppose this is your friend A, this is your friend B, so you're connected like that. Okay, now let's suppose for B we have a multiple friends. For B we have multiple friends. So B have a C friend, D friend, and D friend, and then we have a E friend. Same with the A, we have a multiple friends. Let's suppose G, G, H, and I. Okay, so there is one way to reach C. Let's suppose you can ask A, you can ask A that they both are mutual, because if someone watch his profile, so it shows mutual, because A and B are mutual to C, so it will show that these A is mutual to C. How it is showing? Because A is connected to B and B connected to C, so it will show that A is a mutual to C. Okay, so he can open his profile and send a follow request. So it send a follow request like that. So now now G also connected to C. Okay, and same with the C. If C wants to see the profile of G, it will show the same. B is a mutual to A, sorry, G, because C is connected to B, and B is connected to A, and A connected to G. So B will show mutual to G when C will see. Okay, this is how it will show in a graph data, Facebook. So internally everything looks something like that. So it can be an interest also. Let's suppose B follows interest of crickets. We like cricket. Okay, and if A wants to see like if B follow cricket, so it will show to A also. Kind of a suggestion system. Kind of a suggestion system. Okay, recommendation system, or kind of a this system. Let's suppose A likes B type of reels, uh let's suppose X type X or XY type of reels, then B also showing same type of reels, because A likes AX and B type of reels, then might be B also like X or Y type of reels, because B follows A, so it could be possible that in B's feed it will be show. So kind of this kind of structure it will show, and then in so then we can, so basically same thing, like we can say like we can say a linked list. So just have a single question. So let's suppose you have a linked list. Okay, we have a linked list. So we can say linked list is also a type of a tree. Okay, why we say linked list? Linked list is a type of a tree because suppose we have a tree, and trees look something like that. So trees look something like that. So we call it, we call it as linked list. So it's look like a linked list. Okay, if we try to flatten it, so it looks something like that. So we can say linked list is a type of a tree, because if we can it like a tree with a single child, with a single sorry single child. A tree with a single child is a linked list. Well, you can say here is a root. It's a root. A root have a one single child. Then this is a root. Then it's a single child. Then again single child, single child, single child. So we call it sorry. Same thing here. Same thing here. Let's suppose this is your tree. This is a linked list. And how linked list look? Linked list look something like that now. So we can call it it's a graph. So it's a kind of a graph also. Why? Because it's have a this kind of structure, which is like A node points to B node, B nodes point to C node, C node points to let's suppose E node, then F node. So this is kind of a graph structure. We can call it directed graph. We call it a directed graph. Okay, so it will look like something like a directed graph, or we can say tree is also a directed graph. Why? When tree you can say this kind of structure. So it is a root. So root points to these two children's, and this root points to these two children's. So this is kind of a directed graph. So we can say tree is also a directed graph, but directed graph. But graph cannot be tree. Only all tree are graph, but not all graph are tree. Okay. Like if you're not able to understand this line, but when you start understanding it, like how tree work, how graph work, then you automatically understand this line, like how, why I'm just what I just said you. Or directed graph, cyclic, disconnected, connected, these are all done. And the main question is how we represent a graph in our computer, in computers, in computers. This is the main question, like how we represent a graph in computers. So we know how we already know how tree we can save tree inside our computers, but how, I mean, how we can represent graph. So let's suppose I'm creating a random graph. So let's suppose this is a graph. This is a graph. Oh, this is 1, 2, 3, 4, and 5. This is my graph A. This is a graph A. Okay, but how I will represent in my computer? In our computer, it doesn't know it's a graph. for them it's just a 0 or 1. But how we will represent it? So for representation we have a two methods to represent. So representation means how we save graph in our computer, because conceptually we see it's a graph. In computer we will like in notebook we draw something like this structure, but in computer we cannot draw this structure. We have to save in some kind of a form. So what is that form? So everything save, like we can save in an array also, but we can, here we have a two ways to save. First is like adjacency matrix. We call it adjacency matrix. Okay, we call it adjacency matrix. And second is a list. These are two ways to save a graph in our computer. One is a list, one is a matrix. So we can call it adjacency matrix, adjacency list also. We call it adjacency list. So we can say we can represent graph in a computer by two ways. First is using a adjacency matrix. Second is using a list. So how how they are look inside our computer. So first we will learn about the matrix. So how matrix will look. So for this same graph I try to create a adjacency matrix, then you will understand like how it will save. And like it's a easy thing, not a difficult thing. Okay, just let me share you. So this is a matrix. So how matrix basically looks. So matrix looks something like that. We all know how matrix looks. So matrix looks something like that. So here we, how many nodes we have? We have a 5 nodes. 1 2 3 4 5. So we have a 5 rows and 5 column. So now we have a 5 by 5 matrix. 5 by 5 matrix, because we have a 5 rows, we have a 5 nodes. So for 2, then we have a 3, then we have a 4 and 5. For all, for each and each nodes we have 5 rows and 5 column. So this is for first row, second, third, 4 and 5. Okay, this is how we need to create a matrix. Then how we can, how can we say what is connected to which one? So here in this graph, a1 is connected to 2, 4 and 5. If you notice here, for 1, for these are the edges. So from 1 we have a 1 edge to 2, we have 1 edge to 4, then 1 edge to 5. And if you notice here, this is a non-directed graph. Non-directed graph, because we don't have any, we can see there is no direction, so it's a non-directed graph. Okay, non-directed graph because we don't have any direction here, so it's a non-directed graph. For non-directed graph means from 5 we can go 1, and from 1 we can go 5. It's a road of two lane road. Okay, from 5 we can go 1, from 5 we can go 1, and from 1 we can go 5. It's a two lane edge. Okay, same with the 2, same with the 4, with the 5, same with the 3 and 5. For everyone we have a two lane, we can go 1 to 4, 4 to 1, same thing. Okay, so here how we can represent this, with how we can represent it, we can represent it something like that. So we can say 1. So this is a 1 node 1. From node 1 we have a one connection between 1 to 2. So we can say from 1 to 2 we have a one connection, we can say 1. We fill with a 1. We will say that this is, we have a one node from 2 to 1. Okay, now with the 1 to 4, so 1 to 4 we have one more node. Then from 1 to 5 we have a node. Other one we will fill 0, because from 1 to 1 we don't have any direct call. From 1 to 1 we don't have any road, so we will say 0. From 1 to 2 we have a uh, edge, so we will say 1. Same with the 2. From 2 we have a node to 1. From 2 we have a node to 1, node to 4, node to 3. Then other we will say 0 0, sorry, we will say 1 1 1. Now with the same with the 3. So from 3, so now we are here, 3 to 2, so 3 to 2 one edge, then 3 to 4, we have one edge, then 3 to 5 we have one edge. Other than we will see 0, because we don't have any direct access to the that particular node. Now with the 4, so 4 we have a 1, 1, then 2, then we have a 3, then 5 also. But for 4 to 4 we don't have indirect access, so we will fill 0. Here we will do 1. Sorry, I just missed this 1. Okay, this is 1. Same with the 5. So 4, 5 we have access to 1, with direct access to 4, then we have direct access to 3. Access to 3. Other than we will fill 0. We will fill 0. This is how we will represent a graph in our computer with the help of a adjacency matrix. This is a matrix. Okay, this is a matrix, and this is we call it adjacency matrix. Why we call it adjacency matrix? Adjacency means side by side neighbors. Adjacency means uh, if this is first person and these are second person, so for this person these are two his neighbors. Okay, so that's why we call it agency list. But what agents you have, this is how we call it agency matrix. And for this graph, this is the matrix. And for then we have one more way to save in our computer, which is agency list. List means we have a list rather than matrix. So how it will look, it will look something like that. So this is our nodes, this is our nodes, first node, second node, third node, fourth node, fifth node. These are our nodes. Okay. Now we need to find out what are the agency list here. We need to find a list. So how we will say, we will use let's suppose a 2D vector, 2D vector, 2D vector, a vector with the list. Okay. This is a this is a this is your nodes. Then we will say from 1 we can access 2. So from 1 we can access 2. This is kind of a list. Okay, we can access 2. Then from 1 we can access 4. Then 1 we can access 5. Same thing with the 2. From 2 we can access 1, we can access 4, we can access 3, and from 3 we can access 2, 4, 5. From 3 5. And with the 4 also, for 4 we can access 1, we can access 2, we can access 5, we can access 3 also. And with the 5 we can access 1, 4, and 3. So this is how agency list look for this graph. So if you notice here, so we basically don't use matrix, we mostly use list. Why we use list, why don't we use matrix? So if you notice, in a matrix we need to store some different means we need to store some extra value, but which is this is a extra space. So if you notice here, let me change the color to green. So this is the extra space. We don't need this information. We only need the information which one node to connect to which node. So this is a kind of extra space we need to save. This is all extra space. We don't want this extra space. This is all extra spaces. So we will use agency matrix because it's a more space efficient. It's a most more space efficient. So that's why we will use agency list rather than agency matrix. Okay. So in questions you usually use agency list, or they give you agency list only. They don't give you matrix. They only give you agency list. This is how it will look in, like how it is look, a matrix and list. This is a list. This is a matrix. And this is a non-directed graph. So how it look? But let's suppose we have a directed graph. Directed graph means we have a direction in it. So how we will create for that thing? same logic, or same like easy one, same logic. But suppose this is a random graph, or we can create a same 1 2 4 5 and 3 same. I'm just take the same graph, and then we can add some directions, random directions, add some random directions. So we add some random directions in it. So, or I can just create it a more beautifully. 0 1 4 2 3 5 4. These are the edges, and this is a directed graph. Directed graph, and means we can just add directions in it, some random directions, these directions and these directions. Now we have a direction. Directions means we can only go from this to this, but we cannot go this to this. We cannot go like that. We can only go one direction here, because now we have a direction means we can go from 1 to 2 only in this direction, not vice versa. We cannot go reverse now. So these directions will eliminate that thing. We cannot go reverse, we can go only one directions. Okay, from here, if you notice, from 1 to 5 we cannot go, but from 5 to 1 we can go, but we cannot go 1 to 5. Okay, because we have a direction to this direction. We have a direction with this arrow with this type of direction. Okay, and how will we create the matrix? Adjacency matrix. Adjacency matrix for this particular uh, graph. So same thing, we will create a matrix 5 into 5, 5 by 5. Why? Because we have 5 nodes, so it will definitely have 5 rows and 5 column. 1 2 3 4 5. Same thing here, 1 2 3 4 and 5. So 5 by 5 matrix. Same thing here. So now we need to fill this matrix. How we can fill this matrix? So from 1 to 2 we have a edge. So we will say 1 to 2 we have a edge. Now we have another edge. From 1 to 4 we have a edge. But we don't have any more. We don't have any edge to 5. So that's it. Now it's at now two node, second node. So from 2 we can only go 3. So we can say 3. So from 1 we can only go 3. So yeah, it's done. It's also done. It's also done. Then we now third node done. So from 3 we can go 5 or 4. We will say 4 1 and 5 1, because we can go 4 and 5 with the directions of this direction. So if you notice, we cannot go reverse. We cannot go reverse. So we can only mark whatever the direction it's pointing to. Okay, now from 4 we can go 2. We can go 2, because this direction we can go 2, and we can go 5 also. We can go 5, and other than we will fill 0 0 0 0, because we cannot go there. So we will say 0. We will 0, and same thing here with the 5. We can only go 1, 5 to 1, but we cannot go 4 or 3. So other than we will fill 0 0 0 0. Okay, if you notice here again, we are using so much space. With this is these are so much space we are wasted here, because we don't need this. We don't need that. We can use a list here. So how list will look? So list will look something like that. So this is a matrix, ADJ matrix, ADJ matrix. Then we will create a ADJ, which is adjacency list. Okay, and how list will look? So we have 5 nodes, 2 3 4 and 5. Okay, and from 1 we have 2. We can go 2. We can go 2 and we can go 4. That's it. From 2 we can go 3. That's it. From 3 we can go 4, and we can go 5. From 3 we can go 4 and 5. Yeah. From 5 from 4 we can go 2, and we can go 5. And from 5 we can go only 1. Only 1. So this is how it's this is a list. This is a matrix. So we always use list, we don't use matrix. But yeah, we should know about the matrix also. So we usually use list only. So list is like a important thing, important, kind of important. Okay. And how we will represent, like we know how matrix, we can list or matrix, how we can code this thing. So it's basically a 2D matrix, 2D a 2D sorry a 2D vector, like vector of vector, vector of vector int. Okay, now we call it ADJ matrix. And let's suppose we have a 4 nodes, we have 4 nodes. So it will be like 4, let's suppose we have a n. I'm taking a general term, which is n nodes. So how it will look: matrix of matrix, vector of vector, which is like 4 size, 4 rows. And then we have a vector of int size 4. This is how it will look, a 2D matrix, vector of vector, basically a 2D vector, basically a 2D vector. And list, how a list will look: so you can use unordered map, you can use unordered map you can use unordered map here with int, means nodes. And we can use a int vector of int, because it will look something like that. These are your all list int type of values. And key will be your vector. This is your vector, this is your vector. Okay, these are your vector, this is your value. So this is our key, these are keys, not values, because in map we have key and value. So these are your keys, and these are your values. And values are basically a vector. Okay, this is how you can create a list by using another map. And for matrix, you can simply use the 2D matrix, 2D vector, and it will create a matrix. And here you will use another map to create a list. Or you can use yeah, map will fuck. So this is how it will look. And traversal, and for traversal you basically use DFS and BFS and DFS. This is how they both are look. Okay, so let's try to code like basic structure of the both of these, DFS and BFS. Okay, so let me reshare my screen. So let's create a graph. So for graph we will use a vector of vector. Okay, vector of vector, it's a graph. So how it will look? So these are basically your all type of edges, basically edges. So means we have a connection to 1 2 3, then we have a connection to let me draw a simple graph, then we try to trace back that same thing. So this is your graph. I'm getting a random graph. Okay, 1 2 3 3 4, and then we have 5. Yeah, that's it, 5. Then we have a connection from 1 to 2, means we have a edge here. So 1 to 2, okay, and 1 to 3, and we have a one more connection which 1 2 3, 1 2 3, same thing other. We have a 1 to 5, 1 to 5, then we have a 3 to 4, then we have a 3 to 4. Okay, we have a 1 2 4 edges, and this is how edges will look: 1 to 2, 1 to 2, 1 to 3, 1 1 to 5, and 3 to 4. And we need to add one here. Okay, this is how graph will look, basically edges. Okay, and here number of nodes n will be how many nodes we have. So here we have 1 2 3 4 5. So we have a 5 nodes, and 4 we have a nodes which is m4. Then now we will try to save in our, like, how it will look. So how we can save it? We can we can use adjacency matrix, we can use adj matrix, or we can use adj list. Okay, so matrix simply means a 2D vector. So we can say a vector of vector, which is int. Okay, vector of vector int, uh, adj matrix, and here we have a adjacency list. Adjacency list means we have a unordered map, so we will use unordered map here. Unordered map which is int, then we have vector of int, and we call it adj, call it adj list. Okay, this is how we will save in our, like, how graph will look, how we'll save it. And here we have a n5, which is like a matrix size, so we can define that here. So we'll say n, then vector of int, basic structure which is like n, so it will be like 5 and 5 rows and columns, 5 by 5, n by n, or 5 by 5. And then we have a vector, then we have a list. We don't need to initialize with any value, it's like all dynamic. Then now answer is how we can fill this thing. For filling, we can simply iterate, and then we simply create. Okay, so how we can create that thing? So here we will same thing here, like it will zoom out. So matrix and list. For matrix, we like rarely use matrix, we mostly use list only. So first I will show you list, then we will say matrix. Because matrix we don't use much, like rarely we use matrix, always we use list only. So how we can populate a list? So it's only a map. So how we can say, we need to iterate over our graph. Okay, it's a graph. So auto auto uh, edge, we can say edge also. These are edges now, we call it edges because we have an edge. 1 to 2 we have one edge, 1 to 3 we have one edge, 1 to 5, and 3 to 4, and we have, yeah, 3 to 4. Then we will say edges, and then E means we have a vector of edge, means E means we have a this structure, 1 2 1 3 and 1 4. So we will say int u and int v, because we need two nodes. So basically what are they giving you? 1 and 2 means we have a one edge from 1 to 2. Okay, then we need to connect them means we need to create a list here. So how will it list will look? But I'm saying this is u, this is v, and in my list create a connection between u to v. Okay, so this is your u means this is your, basically this is your map, this is your map. So u means this, u means, so here u means your first node, which is 1. So here you will say 1 1, then make a connection to 2. So 2 will come here, so 2 will come here. Okay, so this will this is basically a, you are creating a list of these type of edges, 1 2 2 3 2 4 5 6, like that. Okay, so here I said u to v. So u, how will you iterate, how will you get the e? Basically you will get I0, because e is a vector, it's a vector na, vector, so vector, so e is a vector. So e first element give you u, and e second element give you v, which is 2. Now you need to create a connection. So if you notice here, this is a non-directed graph, non-directed graph. This is a non-directed graph. Okay, so non-directed graph, if we have a edge to 1 to 2, and from 2 to 1, because it's a non-directed, so we can go like that or we can go like that. So it's a two-way lane. So here we need to save something like that. From 1 to 2 we have one edge, from 2 to 1 we have one more edge here, because we need to consider both the edges. So from 1 to 2 we have one edge, from 2 to 1 we have one edge. Basically we can go from 1 to 2 and 2 to 1. Okay, we need to map that thing. So how we can use another map to save that thing. So same thing here, what we can do here, we will say uh your a adj list of u dot pushback. Why pushback? Because it's a vector, second time is a vector, so vector of u. Okay, here what I did, here I did one map to 2. This is what I did here. Now I need to map 2 to 1 na? So what I will say, I will do adj list v dot pushback u. But I did here, I did 2 map to 1. This is what I did here, because v give me 2, this give me, this is value of 1, and this is a value of 2. Okay, so what I did 1 to 2, so u to v, then 2 to 1, so v to u. So it will basically insert in my map something like that, u to v, because your u is 1 and v is 2, so you will insert something like that. And same thing you will do other, for other thing also. For this one and 3, what we'll do, from 1, from 1 you have a 3, you have a 3, from 1 you have a 3, and from 3 you have a 1. Okay, same thing, same code you will do with this thing. And then we will try to print this this ATJ list to show how it will look. Okay, for auto, we say we can call it anything. Our graph only, graph G or a TJ list, and for list we will say, for here for list, but we can say we need to print our list. So how we can print? So age is a list have G means these are your G. So how will you print? You will simply say for auto e G. It's give a list. What list give you? List, it give you, let's suppose list, call it list only, because ADJ list give you list. This give you the list of all the pairs or all the connections. So you will say list of nodes. Okay, and here you will simply print nodes. Okay, and it will print all the nodes, and here you will add a simple and L to print your values. So let's me run this one. List have your nodes, and then nodes you have your all the nodes with printing. So let's try to run this thing and see, is there any issue or everything works fine. List, what is saying, begin dot list. Okay, we can need to change the name. Let's suppose lst. What is it saying? Begin pair of constant vector of constant pair constant digit list pair. Why it is showing me this vector int vectors? Okay, list is a vector. What? Second guys, no matching functions to begin pair int vector of list. ATJ will give you a list. Yeah, it gave me list. Then what the issue here? To list a pushback. I'm inserting a pushback and then inserting a list of vectors. Single list. Let me try to see out lst with some mark list operators. Okay, why it is not printing? Let me will run. Now it's run, but why it is not printing the thing? So for auto ADJ of list, we have a ADJ of list list. We have a list, then list have all the functions. Auto ADJ list of list push back. It should be a list. What I'm doing, list of vectors. Yeah, vector push values 1 2 root 1. What is not running? Call begin. What is it? Pair of int and list. Pair key and value. It should be give me a key or value. Okay, it's give me a key and value, and v is a vector. V is a vector, and we have to print the key value also. Okay, and it's mean like that. Now it should work. Key and values. Okay, now it's run. So key and value. So key basically the node. So here if you notice, from we have a node from 1 to 2 and 2 to 1. So if you notice here, we have a node from 1 to 2 and 2 to 1. So here we have a node from 1 to 2 and 2 to 1. So here in this metric, in this list, we have a node, we have a connection between 2 to 1 and 1 to 2. Same thing with the others also. We have a connection from 1 to 2 and 2 to 1 to 3 and 3 to 1. So here also we have a 1 to 3 and 3 and 1. See, we have both the connections here. And here also 1 to 5 and 5 to 1. So 1 to 5 and 5 to 1. So this is how it will list look. So this is basically a list we can say. So I can print a ATJ list. This is a ATJ list. This is how a list look. And for matrix, you can simply say for 1 and 2. So how for list, how will you save? So basically you have a 2D matrix. So what you will do, you can simply like simply iterate over your matrix. Okay, int j equal to 0 and j is your n and j plus plus. Okay, and here what you will say my go to. So what are you saying here? So matrix, we have a 1 2 3 and 4, because we have 5 and 5 also. And same thing here, 1 2 3 4 5. Okay, and for 1 we have a connection to 2 from 2 to 1. So what will you do here? So you will say my matrix. So let's call it a matrix, ATJ matrix. So you will how will you populate this thing? You will say ATJ matrix of 1 and 2, make it 1, and then you will say matrix 2 or 1. Sorry guys, I think you are not able to see my screen. I guess now you're able to see. So for 1 to 2 we have this matrix, ATGO matrix. Okay, 1 to 2. So 1 to 2, what we will do, you will say 1 to 2, we have one edge, so you will say 1. Then you have a 2 to 1, so you will add one edge here also, because it's a non-directed graph, so you need to make a both side edges count. So this is how it will look. Same thing with the 3 and 4, 3 and 4, 3 and 4. So 3 to 4, for 3 to 4 you have one list, and 4 to 3 you have one edge. So 4 to 3 we have one edge. This is how you need to populate your matrix. So here you will say it is a matrix of 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 whatever the value you have in your edge. Here you have, this is your edge. Okay, so you need to populate your edge. So, yeah, you need to go to your, you need to say auto e edges int u. So u is your e0 and int v basically your e1. Okay, you get your u and v, and you will say it is your matrix u and v2, and it is a matrix of v and u, make it 1. Okay, and you need to subtract with 1, because in our matrix we have indices start from 0. Okay, so 0 1 2 3 4, 0 1 2 3 4. Or you can just, or you can do one thing, you can just increase the size of your matrix also by 1, so it will remain the same. Or this is how it will, you need to do your adjacency matrix. So you have a u and v, you have a u and v, you got your u and v, then you will add your matrix like that. And same thing here also, and then you will print. So you can print your ATJ here, I, and this is your j, and you can simply print out to show how it will look. See out ATJ matrix, matrix. Okay, and here you will simply present with a simple space, and then after each you will add ATL. Okay, so let's try to run this and see if we got our answer. 1. So you can notice here, this is how our matrix look. You can simply add a new line here also. Okay, so you have created a line to 1 2 3 and 2 2 3, or you can simply add one more 0 also here. So how it will look, so here how it will look, 1 second, let me draw matrix for you, how it will look. Let me clean some. One, two, three, 4 and 5. 1 2 3 4 and 5. Okay, from 1 to 2 we have one edge, then 2 to 1, then 2 to 1, then 1 2 3, 1 2 3, and 3 to 1, and 3 to 1. So 3 to 1 also have one edge, then 1 to 5, 1 to 5 we have one edge, then 5 to 1 we have one edge. Okay, same thing here. Now with the 2, so 2 to 1 we have an edge, then we don't have an edge, so we say 0 0 0, because we don't have any edge now. Then for 3, so 3 to 1 we have edge, and 3 to 4 we have edge, so then we will say 0 0, because uh 1 to 4 we already have, 1 to 3 we already have, and 3 to 4 we have, and 3 to 1 we have. Okay, then same thing with the 4. So 4 to 3 we have one edge. So 4 to 3 we have one edge, other than we'll say 0 0. So we will say 0 0 other than. Same thing here. 5 to 1 we have edge. Then we don't have any edge, so we have 0 0. So 0, we say 0 0. And if you notice, we have the same type of matrix here. 1 0 0 1 0 1 1 0 1. So 0 1 1 0 1. Then 1 4 times 0. 1 4 times 0. Then 1 0 0 1. Then 0 0 1 0 0 1 0 0. So 1 0 0 0 0 1. So 0 0 1, this line. Third line 1 0 0 1. And third line 0 1 0 0 1 0. Okay, so this is how we represent our graph in our system or in our computers. We don't save in this representation. We use this system to create our graph. Okay, I think that's it for today. Like, I don't want to like give you more information. Like we have some algorithm also, but like it will be more to consume. So we can simply, anybody have any doubt regarding this thing, like why we using, like in any way, like